fair that you see an ugly picture of me, actually pre-COVID. So I now have a fuzzy face and longer hair, although my wife is attempting to use the clippers to make me at least somewhat presentable. But I have a background in refining. I've been doing this for a long time, and I am 16 years now with WIKA and Gasco. So I tend to be one of the go-to guys for refining and the multi-point products that we're going to talk about. So as Rick Moses knows, I have about 5-6 days worth of stuff. You guys are going to get only a taste of it, so we won't subject you to everything. But as we start to open up and get to do more, if you have very specific things, a lot of times I have that. So as we go into projects and applications, we can help you out in a much more specific way. So there we go. All right. So today we'll talk about a little bit about why WIKA. Well, what makes us a little different. And so we'll talk about some new things that are going on with us here in the States, and then we'll talk about multi-point thermocouples. And really, we're going to concentrate on fixed bed reactor applications, and we'll talk about the product and a little bit about kind of what goes on. Then we'll talk about a product line, the tube sheet reactor application, multi-points for those, which tend to be very prevalent in a lot of our chemical applications. And then kind of the things that need to be thought about and why we can do that pretty well. And then I end with an easy one, multi-points for gas and sulfur plants, specifically amine. There's one that we do that is really easy, and especially if you have some young engineers and you happen to have an amine plant attached, there's an energy efficiency project that we can put together for a quick, easy engineering win for those folks. So just a kind of a recap. A lot of you will know WIKA. WIKA is one of the largest instrumentation manufacturers in the world. Certainly, we're known for mechanical pressure gauges, but also have significant lines in temperature, level, flow, force, and now density. I'm with the temperature division, and that's where my level of expertise is. I can talk a little bit to the other ones, but temperature is really my specialty. And we are a global organization, lots of subsidiaries around the world, 42 subsidiaries, 75 offices around the world, more than 9,000 employees. So we have a lot of resources in a lot of spots to be able to draw upon. And that means we then have a very substantial presence here in the Americas. So, anything that we can't handle, we have lots of friends that around the world that can add capacity to allow us to do so. And here are some of the offices around the world. Klingenberg, Germany, is outside of Frankfurt, is our headquarters. And then the one on the far right, Atlanta, is actually the Americas headquarters and where all the pressure gauges in this part of the world are made. Edmonton in the middle there is a sister plant to mine and helps with U.S. capacity, and we trade technology and people back and forth quite a bit. My facility is here. This is in Deer Park, Texas, which is just outside of Houston. If you guys are down there, you have to come see either part of your companies or you're coming down to see some suppliers. We are right across from the Shell Deer Park refinery on the ship channel. So on the big ring road, we are about 3 o'clock, where the main airport would be about 12 o'clock, and a lot of the engineering companies are at 9. We're probably 35 minutes from the airport, the big airport, and then 20 minutes from Hobby if you're coming in that way. But come see how we make things. Come see the stuff that's going on. In addition to ETM, we also do level, and then the diaphragm seals manufacturing for the Americas is here as well. Now, one of the pieces that makes us different is we've added research and development to this location. We have a major research and development center in Frankfurt or in Klingenberg, but that's really aimed at pressure. And our R&D facility here in the U.S. is aimed specifically at the process industries. It's a little weird in that we're an instrument company and we built our own process unit. And here's a computer rendering of how that was going to go. Control room here, bottom left. There in the center, kind of laid over, is a fire heater, a furnace, and then the big white tall column is a fixed bed reactor loop. And this is how we initially conceived the facility. Here's a little pseudo PNID. Basically, we've determined in order to make improvements in fired heater instrumentation that we needed to have our own to be able to control the startup and shutdown, to be able to do tests that weren't associated with a customer's timing, right? Because a lot of times that's on a turnaround schedule. We're not beholden to that. We also don't have to worry about damage to the heater, which is kind of a strange thing when you're talking about an owner. But this unit is specifically designed so that we can really mess stuff up and learn how the pieces behave and not really have to worry about it. We do probably 30, 40 turnarounds a year. We'll run Monday, come down Tuesday, do some analysis, and do another test Wednesday, Thursday. So really able to do some interesting things. And we will be doing, for instance, a lot of problem installations, common mistakes. We get a lot of calls from customers, and they said, "Hey, I did this myself. I know I did it wrong. How bad is it?" And right now, my answer is usually, "Oh, that's bad," which is not very helpful. What you'd like to know, especially when we're talking about temperature, is that a 10-degree bad error or a 100-degree bad error? Right? Can I live with it, or do I need to do something about it? And with this, we're going to recreate those over a variety of heat fluxes and operating conditions, so that when you call, we can matrix that and say, okay, well, in our unit, about the same conditions, we got 26 degrees to allow you to make better decisions. And of course, developing products is a key. In addition to the fire heater loop, which we can run by itself, we also go through a fixed bed reactor simulator. This allows us to do improvements on the multipoints and the various supports. And then we have auxiliary loops for temperature, pressure, flow, level. Basically the same kind of thing, except in this case, I can do it at about 700-800 degrees Fahrenheit. So at elevated temperatures. So demonstration loops, product cycling, all sorts of things can be done here. And we are adding some other loops. A coke drum quench simulator, I think, is on the books, as well as some other process units that will get added into this scheme. So this is what it actually looks like. This is a heater that, because of height restrictions, we had to lay over on its side. So it's got a fan in the front, fan in the back, and here's the short stack. But it's a little shy of a 10 million BTU furnace. So full size, and we picked this up in conjunction with Tulsa Heater as one of our partners. Here you can see the reactor skid and the fixed bed before it got insulated. This is a side view of that heater. Again, Tulsa Heater was a partner, and here is our heat transfer fluid that we run through it. We actually boil oil, and Dow is a partner. We use the high temperature heat transfer fluid from Dow that they help us out with. So we had a lot of really good, talented people add in the expertise to make this a very efficient unit. And then this is the reactor pre-installation. We've actually added fiber optics to it. We've got a lot of skin temperature measurements on this, as well as pressure and the multi-points that go in here. So really exciting kind of unit for us. We're learning a tremendous amount about how to operate a process unit and all the things that go on. And we are looking for partners, right? We don't do full utilization of this unit, so certainly we've got a lot of tests that we do. But if this is something that could be useful to you or your company, and you'd be interested in talking about a test, please get in touch with me. Get in touch with Rick. He can put you in touch with me as well, and let's discuss it, because we're looking at advancing not only our knowledge, but knowledge in the industry. And you know, this kind of stuff benefits us all. So in this, coming to you right now, we're doing a lot of work on external skins, both welded versions and then removable. So we've got some great things that will be coming out here in the next 6 to 18 months. Multipoints that we're going to talk about today. We've got some new ones that are on the books as well. And then we are actively doing furnace products. We have some really cool papers that will be coming out on benchmarking standards, as well as performance of some of the products, and then new ones. So again, exciting area for WIKA in the next 6 to 18 months. You'll see some papers first, and then some products to fit very specific applications. And that's really what the key here is, that we will tailor these to the applications that need something special. All right, so that's kind of different, you know, an instrument company running a process unit, but we needed it to be able to make up to these claims, and this is directly from the owner of the company. You say you're a world leader. What are you doing to prove that? And the R&D facility, he gave us a lot of money to be able to say, okay, we can now back that up. And we've been doing the hydroprocessing reactor temperature measurement when we talk about multipoints for a long time. You know, this is actually getting close to 30 years. We'll also talk about the tube sheets, but we also do a lot of weird temperature measurement. So if it's temperature measurement is strange, please get in touch with Rick or myself. Happy to do that. As we talked about, we do a lot of furnace tube skin measurement. We do that for a lot of people. A lot of folks like what we do. That's a whole different presentation. If you'd like to hear that sometime, let us know. Do that, as well as the reactor skins become a whole different ball game, and we have some really great information, but we'll save that for a different time. In the meantime, if you need something, contact one of your Gilson guys or Rick, and we'll put something together for you. Okay, so when we talk about engineered solutions, and that's really what I deal with, is custom-made temperature measurement solutions. There's a bunch of keys to success, and the first one, you know, you got to make the right kind of product. There's some interesting nuances here, but a lot of people will believe that they can do this, and there's some that can. There are some things we'll talk about that this is you need to fully understand the second part, which is the application fit. And these guys go hand in hand, because you've got to make this part work, and then you also have to make the product go into the unit the right way. It has to be properly installed, because we can build and design the right thing, and if you don't install it the right way, everybody's still unhappy. And what we found to getting all this right, we spend a lot of time with our people training not only on product knowledge, but then on application knowledge. So we ask a lot more questions than most. And then we work a lot on client knowledge. There's a lot of different ways to solve any problem, and specific organizations have preferences, and we understand that. And if you're dealing with licensors or engineering companies that have been doing this for a while, they may have a particular pathway they want to go. We can help with that, because we know how to navigate that and to be able to mesh those when there are differences. This gray picture here is actually a hydrocracker in New Zealand. You can see this is a bundle of thermocouples. It's quite substantial. going down from one of the top beds in the reactor, and this is a penetration through the bed. And then you see the thermocouples actually just bend out and around to a measurement point here, and then these other cables are going around to other ones. So this is kind of the first taste of talking about the big multipoints. Multipoints aren't obviously the only thing that you find in a reactor. On the right side, certainly thermocouple thermal wells are still in use, pipe wells, tubing wells, and the pipe well could be vertical or horizontal. And then we're going to be talking about the modern thermocouples, either the linear thermocouples with multiple junctions in a single sheath, or the individual thermocouples that come out and are bent out to individual pieces. At WIKA, we still make all of these. They all have application, and we do specialty variations of all of these. So if you have need, again, this isn't just about multipoints, but we can do the other pieces as well. Now, one of the reasons multipoints became popular, especially in the bigger reactors where we had pipe wells, pipe well has a very specific geometry where you've got a pipe with temperature measurements on the inside as a protection well. Well, you're kind of limited to wherever that pipe is. That's where you can measure, right? So there's big sections that you miss, and there's also a lot of metal mass that's involved in this system. So it takes a long time to heat up that metal and all the associated pieces. So the response time tends to be a little bit slow. For some reactors, this is still the best solution, but in places where new catalysts are coming out, they're more reactive, they're more active. Sometimes you need something that can give you more information, and that's where we're running to. So when we talk about the modern instrumentation, and we refer to that as a FlexSAR, we've been doing this again for a very long time. We use an all-welded construction because of the environments that we go in to make it as durable as possible. It's heavy-walled, large conductor, engineered thermocouples. We provide specialty seal chambers that are high performance, low volume, and then we provide seals on the thermocouples themselves as a additional safety measure. We've done everything from 1 to a little more than 80 sheaths in one assembly. And here's a very traditional assembly, a well neck flange. Here's the seal chamber itself and the valve and detection port, and then the tail end of the thermocouples, obviously where we get hit to the junction box, and here's thermocouples going away. Here's a more unusual one. This is designed for Chevron licenses with a specialty coupling. You can see this is only 4 points, and then remote mounts head. This is armored lead wire. So a whole gamut of different types. And then here you can see some of the installation pictures, and we're going to see a bunch of those. So we do a bunch of different designs, but again, this is why it's engineered solutions, because we tailor fit to what the application needs are. Here's a smaller assembly, very much like the last one. There's that weld neck flange, and here's my seal chamber. You can see it's very low profile, but designed. This will handle 4,000, 5,000 PSIG at reactor temperature, so 800–900 degrees Fahrenheit. And then here are your thermocouples at the top. Similar ones here. Again, they all look a little bit different, but the basic parts tend to be very much the same. So when we do these, and I mentioned engineered cable. With thermocouples, we've known for a long time, bigger is better. You want it to last a long time, put a bigger thermocouple. But that's not really the case. What we're looking for is bigger conductors. The conductors are really where the life of the thermocouple, certainly on the electrical side, comes from. So what we do is have a specially made cable where we maximize the size of the conductors. We've been doing this for a long time and get some tremendous performance out of these. Now, in our design, we actually make one of the legs bigger than the other because that problem leg needs a little bit more help to make it more durable, and these will easily give a reading for 30 years in service, which again can be a little bit crazy, but these were designed to be very, very durable. We also go with a very, very heavy wall thermocouple, which allows us to do that all welded design. Now, this special construction allows us to go to different numbers for sill rather than the standard thermocouple charts. What we did was we actually went out to a third party. BV did an analysis of every thermocouple we had as a multi-point out, and put together this for us. So we did not self-certify, but these are certificates for our SIL numbers. We can do SIL 2 and SIL 3. SIL 3 obviously requires the right architecture, and all the numbers that you would need are involved in the certificate. We also have a full assessment report, how those numbers are arrived at, that any of your safety people can have, as well as a safety manual that again includes the operating instructions as well as the numbers as well. When we talk about SIL, and you know certainly the guys that deal with transmitters know, you got to check all your parts periodically. You know, there is a required proof test, and as we got talking with BV and then some of the other experts at Exita and TUV, they came back and said, hey, you know, thermocouple, we get how we can detect some of the problems, a short or you know, a loss of signal, but when you get some decalibration, what can that do, right? And the fear was if we got some decalibration that could either mask a problem or show a problem that wasn't there, that could be an issue for SIL. So we did our math, and we came up with a proof test interval of 4 and 8 years, because that often coincides with the unit turnaround. And then we developed a way to actually go and re-verify the thermocouple accuracy in situ. This is a quick table out of the operating manual, the safety manual. You can see all the numbers, and here's our probability of failure on demand. The PFD numbers are all listed out. You know, certainly numbers for 4 and 8 years. Again, the end user is always responsible for the math, but you can use the math that you need to make your system work. And then this is one of the early versions of our ability to proof test the thermocouples. We actually put a guy inside the vessel, and he will put a hot box on the end of the thermocouple and drive it to about reactor temperature. Hydroprocessing, it tends to be about 700 degrees, and this goes up there in about 15 minutes. So we've done 22 points, took us about 2.5 hours. It's not insignificant during a turnaround, but it gives you very precise numbers and the ability to determine if your thermocouples are accurate. But then also, because the vessel is open, we can make changes. If you're not happy with the numbers, there's a variety of things that can be done to make sure that you have the proper instrumentation when you start up and you know exactly how it's going to perform. So this has become part of the SIL procedure, and it can be done during any installation or catalyst out time period in these fixed bed reactors. We also do this for a variety of the other applications, liquid filled columns and other bits, but again at an appropriate turnaround. So the first ones went in 1988. Since then, we've done about 140,000 points in service, and you know, we're shy of 3,000 reactors, but we're getting up there. You can see we've done this a lot. Now I have slightly lower numbers also up there, the 70,000 and the 1534, because that's where I had created this table some years ago. But again, the experience list is very much the same. The tough applications, hydroprocessing, hydrocracking, low sulfur numbers has been the lion's share of what we do, but you can see methanation, cumene and styrene, FCC applications, alkylation, all of these we have done. Since this chart was done, the FCC numbers and the CCR numbers have all gone up. but generally the proportions have stayed very much the same. These are the general parts of a multi-point that we provide. Weld neck flange, sometimes a concentric reducer, puck piece, and then the seal chamber itself is up here. We're welded on the front and the back. Everything is connected to a pressure detection port out the side or out the top, and then a box that can be mounted either directly on with a standoff or as a remote mount. Again, these are just the basic pieces, but gives you a very good flavor of what they all generally look like. Now, the important parts, all right, because that's what's outside the reactor, but they're not really doing the work. The important parts are certainly where we're measuring. This is the bottom, the bed exit of a bed 1 or a bed 2 in a multi-bed reactor. Here's the wall of the reactor, and these are catalyst support trays. And you can see here, there's a thermocouple, a bunch of different thermocouples here. These silver lines here are the thermocouple cables coming around. If these are hard for you to see, I've done my job well because I've stayed out of your way. Obviously, there's much more important things going on in this reactor than measuring temperature. There's a certain amount of flow that you've got to get. There's a reaction that's got to go in, and then you also have to get in and out and do work. So if it's hard for you to see these, I'm not in the way. Again, you can kick these and they'll bend a little bit, you bend them back. They are designed to be quite durable and have lasted, again, for 30 years in these type of applications. Now, the full picture has about 22 thermocouples. That should come up where the yellow circles are now showing where all those thermocouples are. Again, if I've done my job, I've kept it out of the way for the important things of what you're doing. Now at the top, we do very much the same thing. This is an inlet, and you can see thermocouples run up, get out of the way, stay out of the way of the spray, and then we just kind of come across and come down on some rods. This is best practice. Again, not real complicated, but very important to making sure that everything works well. And you can see here at the top right, we always leave a little bit of extra because sometimes the drawings aren't completely accurate on here. So as long as I have a little bit of extra, I can use this as expansion and hide it away. And that way, these points during a turnaround are always put exactly where you need them, even if there is some discrepancy in the drawings from what they actually are from what we got. And here's a very common side arm. Sometimes we can weld to the reactor. You can see there's a cladding and a bolted up piece. And here is the thermocouple coming up. You'll notice that the thermocouple is away from the arm. One of the rules of thumb for thermocouples is you want to be 8 to 12 thermocouple diameters in contact with what you want to measure, or 8 to 12 thermocouple diameters away from what you don't want to measure. So in this case, this is an 8 mil thermocouple, or about a 5/16 inch thermocouple. I have deflected this about 4 inches away so that I don't heat sink off of this attachment. You don't want the arm measurement, you want the measurement of the process that's up here. So this is a rule of thumb you'll see in a lot of the installations to make sure that the measurement accuracy is still being maintained. Here is the bottom of a reactor. You can see it starts to be the concave head. This is the outlet collector. A lot of times we'll make a frame to support them, and then the thermocouples will poke up out of the support balls in the bottom, and you see as these do. And you can see that we only need one ring to do multiple rings of thermocouples. So we can try to minimize the amount of support that's in there. Less hardware, less interference, less stuff that you have to worry about. In this case, this ring is actually bolted to the outlet collector. In this case, there's no welding to the wall, so this allows us to do this substantial piece of metal without having any weld work in the reactor itself. And then here is another shot. We looked at the top of some of those beams. Here's from the side. Thermocouples coming in, coming out and around, out to the points. And again, here's one of those expansion loops where we came out and then back down to this thermocouple. Again, anything that had been in a way that they would have had to gone around would have eaten up with this loop, and that's what it's for, to make sure that there are no delays during a installation that would put you off time.
Hey, Robert.
Yes, sir.
We do have a question regarding reactor bed measurements, if you want to hit it right now. It states,
yes, go ahead.
It is common on process temperature measurements to use dual thermocouples within the same well. I know it is possible to do the same with furnace tube skin measurement, but is it recommended, not recommended, or null? Is it an option on reactor bed measurements?
So a bunch of questions there. Let me try to hit that up. So all of us manufacturers have access to dual thermocouples, and there also are triplex thermocouples, but you really don't see that used very often. When we're talking about single thermocouples, remember, the more thermocouple that I put into or more wires I put into a sheath, smaller those wires end up being. So bigger is better. In both the reactor and the furnace, there are occasionally people that will call for duals, more often in the reactor than in the furnace. And so that is completely possible. Sometimes people want dedicated wires going out to maybe safety for one set and information or control for another set. Those are done. When we talk about the 8 mil thermocouple or the 5/16 inch thermocouple, I do a 15-16 gauge wire pair for the single. Because the wire space is reduced for the duals, it goes down to about an 18 gauge. Yeah, again, it's pretty substantial, but very workable. So probably about half the thermocouples out there for reactors are duals, and then half are singles when you really look at the experience list. Very little change in cost when you look at those pieces as well. For furnaces, because we're dealing with much higher temperatures, there is little call for the duals. We don't see that. That's maybe about a 15% of what's out there. Really, your best bet on those is to try to maximize your conductor size. And because I don't need the wall size, so maybe on a 8 mil or 5/16 inch thermocouple with a specialty sheath with the alloy TD type K, I will go with a 14-15 gauge pair to give me actually even a little bit more life. So it's possible to maximize those. So again, for the reactor, always available. Really, that's a user preference. You tell us what you want. You don't see it as much as a furnace requirement because of the lifetime issues. So if I didn't answer that what you wanted, then send another note and we'll take another stab at it. All right, so I'll go on. Or was there any more questions or just that one right now?
That was it. You're good to go. Thank you.
So when we talk about the 8 mil thermocouple, you know, it's certainly a 1-inch nozzle small. We're getting about 4 thermocouples in there. You get up to a 3-inch nozzle, even with like a Schedule 160, you're getting almost 50 individual points in there. So generally more than is really required, often useful. You know, I can make as many thermocouples generally as you need. Now, the other option is to go down to a 6 mil thermocouple, which is also a heavy wall engineered cable and is suitable for these environments and conditions, and we get a lot more. So there are options, but this is a quick table just to give you some ideas of the possibilities if you're looking at retrofitting into an existing unit, and whether it's a fixed bed or a column, separator, you need some more points, this can help. If you don't see a particular number that you need on this, get in touch with the Gilson guys or with Rick, and I can get them tables that are accurate to a wider variety of pieces. Generally, if you've got a bigger than a 4-inch nozzle, I put a lot more thermocouples than you ever want. So I didn't include that on the table. All right. So we talked originally about the response time, and we talked about pipe wells, and I said there's a lot of metal mass. And when I was doing catalyst installations and catalyst startups during reductions, you know, certainly as a process engineer, I'm like, okay, well, instrumentation is always accurate and instantaneous. And I just heard all the I&E guys groan, right? Because they know that's not true. But that's not always, you know, as a process guy, we didn't always know that. And these are good rules of thumb. For the thermocouple thermal well systems, we'll often use a throwdown of about a 60-second response time. And that's to that first step change. This is an industry standard. Obviously, it varies by thermocouple type and thermal well type, and the amount of metal mass. But if you're looking for just a good rule of thumb, that's not a bad throwdown number. The pipe wells, we look at the old heat transfer block or button and guide tube. A lot of metal that has to be heated up. That's about a 3 minute to that first step change. Now remember, that's the 63%. To get the full temperature range, it's about 4 or 5 times this. So, you know, you're looking at about 15 minutes to see the full temperature rise go through. Some of the more modern versions, we call it flexo, which is a bimetallic strip pipe well. Reduce the metal mass, gets that back down to about 60 seconds. The modern thermocouples that we're talking about, because we get rid of the pipe well and you're just using that heavy wall thermocouple, the single sheaths we can get down to about 16 seconds. The Flexar is 4 seconds for grounded, 8 seconds for ungrounded. Grounded, obviously, I'm connected right into the sheath, so I've got a good conduction path. But you can see dramatic improvement in this. Now, what this actually means is here you can see my temperature initiates, and the Flexar, the individual pieces, actually respond very quickly and come right up to about what the temperature is. It takes a while for the heat transfer block to get going because it's got a lot of metal that's got to heat up, right? So it can be quite a long time before your operator or your DCS system actually sees it. So this allows for a lot more response time, especially as you move to making your systems more active and more reactive. And this is really what drove the development of the Flexar. At the end of the 80s, a lot of zeolitic catalysts that were very active came out, and you can melt the reactor in about 15 minutes. You know, certainly you needed to have your operators know about it farther and farther in advance. And this, again, you can see under 30 seconds, that guy has an alarm and the ability to make a decision if it's not already part of the automatic depressurization system. All right. We tend to do a lot of tests, and that's to ensure the product is exactly what you need in service. You know, the cable comes in and we do a bunch of tests on it. Our suppliers, both internally and externally, yeah, because we do actually have an MI cable manufacturer that makes some of our cable, and then we get a lot from some trusted suppliers that we've had for more than 30 years. But they do a lot of the tests, so they'll actually look at a calibration on the equipment, and then we'll look at it to make sure it's in the right category. And then we do a bunch of function tests, installation tests, X-rays, before we even ever assemble it into the multipoint. And then once it's in the multipoint, we do pneumatic and hydrostatic tests, because a lot of these are in pressure situations, as well as dye pen and X-ray. And then now, as you saw, we've added the in situ verification. So once it's been shipped and bent and unbent and installed, you get a final verification of how that product is going to perform in your vessel itself. All of these are available if we're doing a project for you and you want to come watch them, or have a designated inspector come see those. Happy to do that, arrange that with a project manager. Love to have you guys down. I will say that, you know, a hydrostatic pressure test hopefully is about like watching paint dry. You know, and but again, come see it, verify that we're doing what you want, and I think you'll be very happy with what you see in the facility. Now, for those of you that have some of these, what are people doing? Well, really, you know, we're looking at operating the reactor. We're trying to keep it below catalyst problem temperatures as well as metal temperatures in the reactor. But then also sometimes you're saying, how well am I doing? Can I look at maldistribution? And there are a bunch of different ways here. You can see, you know, guys like Tracer Co. and some of the others provide radioactive tracers. There's a bunch of records evaluations you can do. But if you have enough thermocouples in there, you don't need to call anybody out. You actually have all the equipment that you need. And if we talk about a pulse test and, you know, just a single bed reactor here with a bunch of thermocouples in it, some catalyst, a distribution tray, some topping material. This is, you know, a very simplified reactor, but you have all this already. So what you do is you induce a slight temperature bobble in your process, and then you watch how the temperatures move through the reactor, vary radially, and then how they vary across the gradient, as well as the time that it takes to get there. So once you know the variation and the time it takes to get from one level to another, you know, of the temperature change, you actually have everything you need for a flow map, right? So you don't have to go out to anybody else. This is something you can do. Your process engineers can do to ensure, hey, was your loading right? Is any of the internals causing some issues? And you can come down with enough thermocouples. I've seen guys recognize that there were hard hats, you know, inadvertently left in the reactor, or the loading was dished or mounted. Anything that would be causing you not to get the maximum performance, you actually can find out. So this becomes a really nifty tool once you have the thermocouples. Now, the thermocouple here, you can see we provide a regular thermocouple, although it is beefy and designed for the application. And then we add a fitting at the back. Now this is a standard swedge lock fitting, really, that our transition is made out of. Not the normal tubing, right? But this is designed to hold pressure. So in the event that the thermocouple was breached, it is possible for the fluid to actually wick through the MI cable. It will hold pressure. We've taken these up to 3,000 pounds of light hydrocarbon, cut open on both ends to see if we can blow out the innards. It does not happen. You get about a 1 drop weep every 8 hours, so about 30 milliliters every 8 hours. So not substantial, but you will have process that wicks out here. What you can do is cut these wires, spin on a standard swedge lock cap, and you've maintained the integrity of the reactor. The multipoints, the linear multipoints, you can't do that. There's too many wires. This is made out of tubing. If you try to cap this, generally it'll explode. You have to manually cut this off and then seal back here. So this is only available on the individual thermocouples. But that only happens if there's damage to the thermocouple, and the damage to the thermocouple, because these are so beefy, tends to be made during a turnaround. So welding, grinding, shearing events. If somebody tells us, because these are so big, we actually can weld a splice back together. Instead of having to order a new unit, which could take weeks, or send it back to the factory for repair, send a technician out. The pieces can be identified. Remember, these are 15, 16 gauge wires, so they're very easy and large to identify. The wires are reattached. Aluminum oxide is packed back in, and an oversheath is drawn over the top and then welded at one end, heated up to drive off the moisture and cure the insulator, and then weld the top end. We've had these running for more than 15 years. Once we get done, we actually do that in situ verification to verify exactly what you're getting, so that this is correct and accurate before those technicians leave and you start up the reactor. So doesn't happen very often. You know, at that point, we had 90,000 points. I think we've done about 450 of these now. So again, when you're talking about 150,000 points, 140,000 points, it doesn't happen very often. But if it's yours, you don't care how often it happens. You just want to know that there's a solution path to fix it. And we thought that through. We have one of those. It's tried and tested. All right. So that's kind of the fixed beds. The modern ones, again, like I said, we make the pipe wells, we make the linears. We're going to talk now a little bit about mini multipoints and optimized multipoints, which is these are very popular in the chemical applications. So let's talk about tube sheets real quick. You'll see us do a tremendous amount of the acrylic acid reactors around. Phthalic anhydride, acetic acid, ethylene, propylene, syngas. You'll see us in a bunch of those. So a good experience in history. Again, when we talk about tube sheets, you know, like acrylic acid, we've been doing this for more than 20 years. We did the largest training in the world in Saudi Arabia. I think there were more than 1,600 measurement points. And typically we're doing that with mini multipoints or OMPs or traversing pipe wells. And then if you think about this, these tube sheets, essentially an SMR is the same thing. It's a furnace environment, but we've been doing SMR measurements, again, for quite some time. Even at those extreme steam methane reforming temperatures, you know, because their equilibrium temperature is 1550 Fahrenheit. We get 10 plus years if we do it right. We're able to get out and do fixes for people, and Chevron, Praxair, Air Liquide, a host of others. We've done that. So when we talk about tube sheet reactors, and these are tubes filled with catalyst, you know, some of the questions that come up, because this now is not trivial. How do you keep the thermocouple array in the middle of the tube during loading? How do you load catalyst when now I got a thermocouple in the way? Because you know that's not normal for your tubes. And then how do I verify that this is accurate? Maybe with a pressure drop test if the thermocouple's in the way. And of course, when we're measuring, we want that thermocouple to stay in the center the whole way, because if it tends to get off center, again, I can have some areas that can be problematic in that tube. So here, if we look at you know, a fixed a tube sheet reactor, right? So a bunch of tubes. Here's the top of the tube sheet. Here's the bottom. Very much like an exchanger, you know, kind of upright. Process is going to come in here, go through the tubes, do a reaction, and obviously there's a media that's in here, either heating or cooling, depending on what type it is. How this all goes together becomes really important, right? Because you take the top head off, sometimes you take the bottom head off. Well, if my nozzle is attached to this top head, I can't have it in place to put the thermocouple in. That becomes a problem. So how do I do that? A lot of people will solve that by putting an extra little puck piece, some piping, that I can have a nozzle out the side. But now I've got to protect the thermocouples as they go to the individual tubes. And a lot of times we're going to do that with a guide tube. There are other ways to make it come out the top head. We done internal flanges, specialty seals. But again, thinking through the sequence, I've got to put the thermocouple in, then I've got to load catalyst, then I've got to pressure drop it, then I've got to put the top back on, is something that you don't find with you know, thermocouple thermal well. That's this is unique to these, and we've done a lot of work to make this so that it is doable. We actually have created specialty equipment to center the thermocouple during loading, and to allow for the pressure drop. You can do a variety of different things. There can be spiders, there can be some metal spikes on the thermocouples to keep them in the middle. Generally try to avoid those because they may lead to your catalyst bridging and not falling all the way through the tube. And then so I don't have enough catalyst in one tube versus another tube, right? Generally, there is no flow control on these. It's all exactly like an exchanger. So we want to make sure that every tube has pretty much the same amount of catalyst and pressure drop that every other tube has, so the flow is even and you're getting full utilization. So again, we know how to maximize the points. We work with the installation crews to make sure this can all be done, and that you can do all the things that you need to do in the application. Again, it's that whole philosophy. Temperature measurement isn't the most important thing for you. You need it, but you know that those vessels have to do some really important things, and we need to be able to work within the constraints of what you need to do. The multi-points are pretty easy. Again, a bunch of either small thermocouples inside an outer sheath, or multiple wires in here that are all connected at different elevations. Typically, you'll see them up to about 25 feet, but certainly longer ones are available. Lead times can get a little bit longer on those, right? But these are more available. And then sizing, you'll see in these, it's not uncommon to be, kind of in this range on sizing, although it can get much smaller if required. But now we need to talk about life and how that can go. And if we're dealing with individual thermocouples in an outer sheath, obviously O30s become quite easy, either grounded or ungrounded. As we get down below O30s, you can get down to O10s, but typically ungrounded becomes very difficult with those, so they tend to be grounded. So a lot of different varieties. 7 is the most common number of thermocouples in these because it's an ideal packing. One thermocouple with 6 around it and then an outer sheath. Here's a drawing from one of those acrylic acid type reactors. In this case, there's a 7-pointer going in from the top, as well as a 7-pointer that goes in from the bottom. They're actually tensioned together so that there is no support hardware. Very interesting design here. Again, experience. We've been doing these for a long time. Took a long time to get to this point. But in the days, we've also done in those reactors traversing thermocouples. So the same kind of thermocouple, but with a motor actuated top. And that could be a control out on the unit, as well as a control in the operating control room that allow you to have maybe 7 points that are fairly close together and optimize where you put them. They could be pushed farther into a tubing well to see temperatures maybe farther into the reactor, or pulled farther out. Again, there are some people that use these. This is another one of those options for you. All right, so let's talk about the last one. This is really easy. A lot of folks have contactor columns. One of the best examples is that you've got a contactor and a stripper in an amine plant. Certainly we do a lot in hydrogen, methanol, ammonia plants, but also sulfur and gas plants. A lot of folks have these. And you can see here the columns over to the right side. Here's a little bit of a schematic. On the left, I've got my contactor. I've got the sour gas, the acid gas stream coming in the bottom. That goes up the tower, gets cleaned up, and sweet gas hopefully is going out the top. And then I've got lean amine coming in the top and raining down, making as much contact with the acid gas as we can, and going out saturated as rich amine to go around to the stripper column. Now, there is a heat of absorption that goes on here. And what we'd really like is that most of that absorption to be about 1/3 of the way down the column. That allows the top of the column to be used for polishing. Problem is, a lot of these didn't have any instrumentation. They had an in and an out. And there was a Chevron facility that was seeing that operators would basically turn up the rate of the lean amine to make sure that this reaction was happening close to the bottom of the tower, which was meaning the stripper column was having to run harder. You're having to put more heat because you had more flow through to accomplish what it needed to do. We came in through a bottom nozzle that was available, a less than 1-inch nozzle, and came up and did 21 points going up through these perforated contact trays. They were basically held on with little attachments, at trays, and I think they measured every other tray in the column. You have to do this when you're retraying, because there is a way to fit it all up in an order that has to go on. But this information then allowed the operator in the control room to optimize where the actual heat of absorption was happening, or the bulk of the absorption. That meant he was optimizing the rate and the stripper column heat, which resulted in a pretty good energy efficiency project for that plant. And we've done this several times. Again, it's not real complicated. These are not very expensive multi-points. It's a pretty simple project, and can be really good, especially if you've got a new engineer coming on, gives them an opportunity to deal with some instrumentation, some specialty suppliers, and get a good win under their belt. So again, very simple, but gives you kind of a taste of some of the problem-solving things that we can do. If you need, as you saw, Gilson has some pretty good documentation that they have some of our documentation as well. Please, if you need it, just reach out and holler. If you need something else, that can always be available. Again, on these, we recognize that this is just a starting point. Engineered solutions often are going to require some additional information and maybe some specialty stuff, and that's what we do. So please just ask. All right.